Okay. We are looking at cell potentials under non-standard conditions. So standard conditions or standard potentials assume concentration of 1 molar. This Nernst equation allows us to calculate potential when the two cells are not 1 molar. So going through just the basics, you got your R, temperature in Kelvin, number of moles, and Faraday's constant. Things we've all talked about before. Where it comes from, you've got your normal delta G. Delta G is also equal to the negative NF of E. You can plug that in, solving for your delta G again at the normal cell. And then you again have your E cell coming across here. You don't have to derive it, but it does help if you understand it for you to get it through what each of those mean. Simplified though, because we have some of the same constants, we have this 0.0592, you might see 0.0591, not really equivalent. And then remember, n is the number of electrons, and this is the log of Q. Okay, because it's not going to be at equilibrium, it's going to be at something different. So, Nernst equation done a little differently. So when we have standard conditions, you get your 1.1 molar. We've done this with zinc and copper before. Not at standard conditions, we can see that we can have different concentrations, and that'll actually get us a slightly higher voltage. So these differences can make a difference, and sometimes you actually want these different conditions for a variety of reasons. So equilibrium constants and cell potential. Equilibrium, they both happen at the same rate. The battery is dead. There's not a lack of chemistry in a dead battery. The fact is that the rates of reaction are the same, so therefore you don't have any voltage. Again, 0 volts. So if we think about the Nernst equation at 25 degrees, we have the standard, because then we know what the standard is because it's 25 degrees. And it's equal to 0 volts. So knowing that, we can determine that this cell is equal to this times the log of K. So we can calculate the equilibrium constant from the cell potential. We have this zinc copper example, 1.1. We know it's 2 electrons again from the number of electrons that are oxidized or reduced. Solve for your K, and we can see that this occurs at a super high rate. So this is a really good cell potential. Now you can also have what's called a concentration cell. Both sides of the cell, same components, but different concentrations. You can see this one's 10 times as concentrated as this one. Again, same metals. What kind of voltage would occur? So first you need to decide which goes oxidation, which goes reduction. Because again, they're both at the same, but one's going to happen over the other. The 1 molar is going to decrease in concentration, and the 0.1 must increase in concentration. So we got to think of what's going on there. We have the higher amount of ions in solution, right? Higher concentration. So that means it's going to reduce and become more zinc metal. On the other hand, this is going to become oxidized and increase in concentration. So in the end, this will go dead when the concentrations are equal. Because if the concentrations are equal, everything is equal, no voltage difference. So the higher is going to decrease, the lower is going to increase, and they're going to meet in the middle. So calculating this. All right, so we have our ideas of all of our information, 1 molar and 0.1. That tells us this is the product and this is the reactants. So we know which we're going to put in for our Q. So again, you've got your values, 2 electrons because it's zinc with its 2 electrons, 0.1 over 1, do the calculation, because remember, E naught is 0. There is no example here because they're the same oxidation reduction. They cancel out. So therefore, we're going to produce a very small voltage of 0.03 volts. So that's where we need to think of a concentration cell, is thinking of which one's product, which one's reduced. And so we can tell the lower concentration is going to be our product, higher concentration is going to be our reactant. So our log is always going to be less than 1 because it has to be. Okay, otherwise you're not going to be able to get that value. And if that's less than 1, if I remember right, that makes it a negative value. So because this is being subtracted, that's going to make this a positive value and actually have some voltage going on. So quantitative is nice, but qualitative is used for explaining, and that is also talked about on the AP test. But remember, these are for when it's not 1 molar, not 1 atmosphere, or not at 25 degrees Celsius. The biggest mistake that students have done is try to utilize Le Chatelier's with these. This is not at equilibrium. If it was at equilibrium, it would be 0. But the whole concept is it's not. It's creating a voltage. It may look like nothing's changing, but there would be growth at the cathode and loss at the anode. And the charges are constantly flowing one direction, not both. So if we kind of take a moment to look at these. So let's look at this in action. So when a redox reaction occurs at standard conditions, meaning Q is equal to 1, then the non-standard and standard are equal. Because when log of 1, that equals 0, this whole part goes away, and the standard of the cell, or the energy of the cell, is equal to the standard energy of the cell. When Q is less than 1, then that means the energy of the cell is going to be greater than this, and that's because of the idea that this is, let's say, a positive value. If Q is less than 1, this value is going to be negative, so minus a negative, it's going to make it a larger value. When Q is greater than 1, that's going to make this a positive value, so something minus a positive value is just going to be smaller, so the energy that's not at standard is going to be less than. When Q is equal to K, there's no tendency in either direction. Because when Q is equal to K, that's what this equation is. This equation here is E cell at the standard. So that minus itself is 0. Okay. So again, that's what's put here, is that when you have the standard potentials when Q are 1, standard potentials. As the system reaches equilibrium, the magnitude of the cell potential decreases, reaching 0. So it's going to slow down. Having conditions not the standard, it will take it further from equilibrium than Q equals 1 and increase the magnitude of the cell potential relative to E naught. Having conditions not the standard will take it closer to equilibrium, then Q1 will decrease the magnitude of the cell potential relative to E naught. Again, read this again here, but this is showing it in action. This is something that will come up somewhere on there, because the idea is that you're trying to understand how these different cells function based upon it being not at standard conditions. However, because again, when are batteries always at the same standard conditions? Now our last bit comes from the concentration cells. Remember, these half reactions are identical, and the standard cell potential therefore is 0, because again, standard minus standard equals 0. Right? Now, because of the different concentrations, they must be calculated using the Nernst equation. So we know that this is going to be 0 because, again, it is. We have our 2 electrons because we can see our 2 electrons from the original balanced equation. And then we have our change in the differences in concentration, with the smaller one always being on top, which is going to give us a positive value. Because when you have these in different concentrations, there's always going to be some flow of electrons. And if there's a flow of electrons, awesome. You get the idea of a positive voltage. Larger the difference, the larger the E cell will become. Electrons flow from the lower to the higher concentration. This change in concentration of the ions in solution until both become equal and then 0, all the time decreasing towards 0. Because again, this concentration is going to decrease, it's going to increase, that voltage is going to change over time until eventually it equals 0. So again, concentration cells, not a very high voltage, but can be handy when we're trying to look at small voltages. Coming with any kind of questions, take care, and I'll talk to you later. Bye-bye.